In this video, we will analyze the actual envelope detector circuit, which will be used to detect the envelope of an amplitude modulated signal V of t. So before we look at the actual envelope detector circuit, I want you to recall the step response of an RC circuit for a general step input V in of t equals AU of t and some initial charge V out of 0 on the capacitor. In general, V out of t is given by A plus V out of 0 minus A times e to the minus t over IC, and this whole thing times U of t. So, if the capacitor is initially uncharged, which means V out of 0 equals 0, and we apply a unit step function AU of t, and where A is not equal to 0, then we get V out of t equals A times 1 minus e to the minus t over IC, which is the same step response that we derived in Lab 1 for charging of a capacitor. On the other hand, if the capacitor is initially charged with some charge V out of 0 is not equal to 0, and it's discharging, so A equals 0, then V out of t equals V out of 0 times e to the minus t over IC, which is the exact same response we derived in Lab 1 for discharging of a capacitor. Alright, so what does the envelope detector circuit actually look like? The envelope detector contains a p-n junction diode and a resistor in parallel with a capacitor. So here's our input voltage, V in of t. We then have a p-n junction diode, and then a resistor of resistance I in parallel with a capacitor of capacitance C. And the output voltage is taken as the voltage across the capacitor. Now, in order to see how the envelope detector circuit works, let's analyze the circuit for the cases where the diode is forward biased and reverse biased. Now, for simplicity of analysis, I'm going to assume temporarily that the turn-on voltage of the diode is 0 volts. So case 1. If V in of t minus V out of t is less than 0, which means that the diode is reverse biased. A reverse biased diode is equivalent to an open circuit, which means that our envelope detector circuit can be replaced with an input voltage V in of t followed by an open circuit and then our IC configuration. So this is simply an RC circuit where the capacitor will discharge through the resistor. And so this tells us that if the input voltage of the envelope detector is less than the current output voltage, which is also the voltage across the capacitor, then the capacitor will discharge through the resistor and the output voltage will continue to decrease until it reaches the input voltage level. And this capacitor discharge will occur with time constant RC. Now case 2 is that V in of t minus V out of t is greater than or equal to 0, which tells us that the diode is forward biased. Now, using the piecewise linear model, we can replace the diode with an ideal diode, a voltage source, and a resistor of resistance ID. Now, since V in minus V out is greater than 0, the ideal diode is simply a short circuit. And as I said earlier, I'm going to assume temporarily that the turn-on voltage of the diode is 0 volts, which means we can replace the p-n junction diode with a single linear resistor ID. And so our envelope detector circuit becomes an input voltage V in of t followed by a resistance ID and then another resistor in parallel with a capacitor. Now, before we continue with analysis of the envelope detector circuit for the forward bias case, I want to show that assuming RD is much less than I, we can replace this circuit with the same circuit but without this resistor I. So we're going to assume that ID is much less than I. I'm going to first derive the frequency response function of this forward biased envelope detector circuit, and we'll do that in 2 steps. Step 1 is convert the circuit to phasor domain. So in phasor domain, we'll have our input voltage phasor, V in phasor, a resistance of ID, another resistor of resistance I, and then the capacitor, which has an impedance 1 over j omega c. And then our output phasor is taken as the phasor voltage across this capacitor. Second, I'm going to use voltage division to relate the output voltage phasor to the input voltage phasor. So we have V out phasor using voltage division equals this impedance, which is I in parallel with 1 over j omega c, over the total impedance, which is ID plus I in parallel with 1 over j omega c, times the input voltage phasor, V in phasor. And this equals 1 over I plus j omega c over RD plus 1 over I plus j omega c, and this whole thing times the input voltage phasor. And so if we take the ratio of the output voltage phasor to the input voltage phasor, we get that V out phasor over V in phasor, which is by definition the frequency response function h of j omega, equals 1 over I plus j omega c over ID plus 1 over I plus j omega c. Now I'm going to multiply top and down by this denominator 1 over I plus j omega c. And if I do that, we end up with 1 over 1 plus ID times what I multiplied by, which is 1 over I plus j omega c. And if I expand this out, I'm left with a frequency response function of 1 over 1 plus ID over I plus j omega ID times c. Now, assuming that ID is much less than I, this is equivalent to saying that the ratio ID over I is much less than 1, which means that 1 plus ID over I is approximately equal to 1. And if we use this approximation, we get h j omega is approximately equal to 1 over 1 plus j omega ID times c when ID is much less than I. And if I compute the frequency response function of the forward bias circuit without the resistor, we have our input voltage phasor. We have our diode resistance ID and just a capacitor, no resistor I. And then this is our output voltage phasor. So this is the phasor domain circuit. If I use voltage division, I get V out phasor equals this impedance 1 over j omega c over the total impedance, which is 1 over j omega c plus ID times the V in phasor. And if I multiply top and down by j omega c, what I'm left with is 1 over 1 plus j omega ID times c times Vn. This means that the ratio of the V out phasor over the V in phasor equals 1 over 1 plus j omega RD times c. And this is the same frequency response function as the frequency response function of our original forward biased envelope detector circuit, using the assumption that ID is much less than I. And it turns out that this assumption that ID is much less than I is actually a pretty good assumption. For instance, when you build the envelope detector circuit in the lab, you will use a resistance I equals 1 megaohm. The forward bias resistance ID of a diode is generally on the order of around 100 ohms. So the ratio of ID over I is 10 to the minus 4, which means that ID is 4 orders of magnitude less than I. So definitely the assumption ID is much less than I is a valid assumption in this case. Alright, so since that's a valid assumption, I'm going to continue analyzing the forward biased envelope detector circuit using this circuit here without the parallel resistance I that was in parallel with the capacitor. So for the forward bias case, our envelope detector circuit reduces to a single resistor of resistance ID in series with a capacitor. And so as we can see, if the input voltage is greater than the output voltage, which is also the voltage across the capacitor, then due to charging of the capacitor, the output voltage will increase until it reaches the input voltage level. And this charging of the capacitor will occur with time constant RD times C. So in the next video, we're going to sort of put the results of the reverse bias and forward bias cases together to see how the envelope detector circuit as a whole can detect the envelope, and we'll also look at 4 different conditions that must be satisfied in order for the envelope detector to reasonably detect the envelope.